So I hope you had good holidays. And I'd like to start by recalling what we did 2 weeks ago. So what we were doing was called the quantum Teichmüller theory. And I'd like to recall what was the equation we were solving last time. So, so we had started by the equation of the form for the unknown operator W hat, which satisfied effectively homogeneous linear equation, but we write it like a conjugation equation, but you always can put the inverse of it to the other side to make the system linear. So it was like this, W minus 1 with index h bar acting on a hat. So the equation for unknown operator W hat in L2 of R2. So let me recall what was here A hat was something taking 4 possible values. So it was either e to the power 2 pi b qi or e to the power 2 pi b pi, with I taking values 1 and 2. So p1, p2, q1, q2 are Heisenberg position momentum operators with commutation relation Pj, maybe it's better, Qk commutator was 1 over 2 pi I for imaginary I, delta Jk. And W done in a parenthesis with index, subindex h bar was a algebra automorphism of the algebra generated by those A. And let me recall you what it was defined. So W minus 1 h bar acting on a couple of, okay, so I use the notation I had last time. X1, X2 hat was given by X1 tensor X1, comma X1 tensor X2 plus X2 tensor 1. So I will explain what are these symbols are. W minus 1 sub h bar acting on 1 tensor x1 hat, 1 tensor x2 hat was x2 hat tensor x1 hat, x1 tensor x2 with hats plus x2 hat tensor 1 minus 1, 1 tensor x2 hat Yes. Same inverse guy. x2 plus x2 tensor 1 inverse. So where, so we identified x1 hat tensor 1 is realized like E 2 pi b q1. x2 tensor 1 is realized like 2 pi b p1. Right, because tensor component in the first tensor component corresponds to index 1 on the level of QP operators. And index 2 for the second component, which means that 1 tensor x1 hat is a E 2 pi b q2 hat. And 1 tensor x2 hat is a E 2 pi b p2. So you see that the meaning of some sub-indices for x's and for q's and p's are completely different. Because meaning of 1, 2 here just to enumerate them, to distinguish between x1 and x2. While here the meaning of 1 and 2 is more broad. They indicate in which tensor component the operator acts. Okay, so everything this was done last time, and we reduced the system of 4 operator equations to something looking very simple in the end. So we have seen that any solution of how it was called in the system. Okay, never mind. It was star is of the form W hat equals phi of Q1 minus Q2 plus P2 as argument E minus 2 pi I P1 Q2 for a function phi mapping R to C such that what's going on? Sorry. Such that it admits the analytic continuation. I think that because analytic continuation is always unique, right? If it exists. The analytic continuation to strip of the strip, how to say it, is S given by Z in C, such that imaginary part of Z is this less than some number, W, or no, H, with H bigger or equal to B. It should be analytic at least in a strip at least of width bounded by the parameter B, which is here. quantization parameter, and where it satisfies the functional equation and the equation was a phi of x minus I b over 2 equal 1 plus e 2 pi b x times phi x plus I b over 2. So you see from the equation why we have this restriction for the width, because we should be able to go in imaginary direction at least by half of b upwards, and likewise half of b downwards. So in total we have a width twice half of b. But of course it might be analytic in a wider strip, because this equation still makes sense there.
So h is greater than or equal to b over 2?
Sorry?
So h is greater than or equal to b over 2?
Yeah. Thank you. Because it's a half, right?
But when you be strictly larger than b over 2?
It can be, it will be, we will see.
No, but you already also assume that, because otherwise it's not defined if it's just equal to b over 2.
Sorry, I'm not sure.
If h is equal to b over 2, you cannot go to the plus bi over 2.
Well, usually what we say that function analytic in an open domain, but continues on its closure, right? So, yeah, maybe you're right, but I would say that even equality is admissible, because we just go to the boundary, right, by continuity, and this still makes sense. Okay, so that's what we had last time, and now I would like to comment on this equation, at least to say that it has a functional theoretical meaning just by going a little bit back to the derivation of this equation, just to go making one step back from this final equation, which operator equation preceded it, right? From where we derived it, and we will have a spectral theory interpretation of that equation. Okay, so remark. Today is lecture number 9, so maybe 9.1. So the spectral theory interpretation of double star. So if we go back to the operator identity, which led us to this equation, then it looked like this: E minus pi b q, no, p, sorry, p phi inverse of q, phi q inverse, E pi b p phi of q. Here twice, right? But we wrote it like pi b p, and once more pi b p, E minus pi b p, and all that was equal to 1 plus E 2 pi B Q. Right, that's an equivalent form. Is an equivalent form of double star. Why it was so? Because we used the Baker-Campbell-Hausdorff formula to first write this like a phi. So if we conjugate an operator by something, usually by unitary operator, then we can conjugate the argument, right? If it is a operator, the argument is an operator. But on the level of polynomials, we can conjugate by anything invertible. And this principle still works. So if we pretend that this holds true for this conjugation here, despite the fact that this is a positive unbounded operator, so we put it inside. And then use the Baker-Campbell-Hausdorff, which says that this is equal 1 plus pi b p q hat commutator, and so on. But the tail is trivial. PQ, the commutation relation is known. So this is equal q plus pi b 1 over 2 pi I. And then we simplify. We get q minus I by b over 2. And this is how we found this guy. Likewise for the first one, but it is inverted. We put it on the other side and then forget that q was operator, just putting to its eigenvalues. That's how the equation came out. But now let us not do it this way, but just to return to original form of that equation by putting these guys back to the right-hand side. So this is equal phi q minus 1 e 2 pi b p. So I collect back these two guys together. Phi q and equal, and this guy go back to here. So the result will be e 2 pi b p plus e 2 pi b p plus q. Remember, I did this remark last time that when we multiply by two non-commuting guys symmetrically from two sides, in the case of Heisenberg operators, when the commutator is central, nothing happens like quantum. So e pi b p e 2 pi b q, it's multiplied from two sides. This is just if you multiply commuting things and put together. Because this correction scalar factors coming from combining these two and combining these two are of opposite sign and cancel out. Okay, now here is the equation. Triple star. And it has a spectral meaning. So let us look at the right-hand side. So what we see on the right-hand side of this equation. So in the right-hand side of triple star, we have a self-adjoint operator. Why it is so? This is positive self-adjoint, right? Because P is easily diagonalized by Fourier transform. So it's spectrum just positive half line. So it is positive self-adjoint because it's a real exponential of self-adjoint. Same here, because this is conjugated to this easily by Gaussian exponential. And the sum of two self-adjoint operators whose spectra are bounded from one side, for example, two positive self-adjoint operators, their sum is self-adjoint. This is a fact in functional analysis. If we had here minus, then the conclusion would be wrong. Because when we put minus here, so we add one positive operator with a negative operator. So from both sides, we don't have any bound for the spectra. And this spoils the conclusion of self-adjointness of the sum. But luckily, we have a plus, and so the conclusion is that, so in a strict functional analytical sense, this is a positive self-adjoint operator. Okay, and now, looking at the left-hand side, in the left-hand side, star, we have a conjugation of another positive self-adjoint operator with well-known spectral decomposition. Because, as I said, so this exponential is easily diagonalized just by Fourier transform. So to write a spectral theorem, it's trivial here. And now if we assume that our phi is unitary, then this equation just tells us that we have a spectral decomposition for the right-hand side. Right? We conjugate by unitary operator something known, and we get an operator for which a priori we don't know how to solve the spectral problem. It's much more difficult. So, it's not linear, at least, right? Here we could just take a log, and then this is a spectral problem for the operator P. But here, no way to take a log, at least directly. But if we would know what is phi, then this is equivalent to solving the spectral problem for the operator in the right-hand side. So, to find a unitary phi of Q is equivalent to solving the spectral problem for the right-hand side. And yeah, so There is a functional analytical guy called Varanovich who approached this problem from that side, functional analytical. And so you can look at the literature in principle if you want. I can give you the reference. But what we will do here, we will proceed with the functional equation. And actually, so what we have, we already have more than just the spectral problem for the operator, because we have concretized the structure of the conjugating operator, that it is a function of just of Q, nothing else, right? If you forget about the right-hand side, just address the spectral problem for that operator. A priori, you don't know why the conjugating operator should be just a function of Q. Right? You should just honestly proceed by writing, making sense for that operator, its domain, and so on and so forth. But we came to a conclusion already with extra information about the conjugation operator, that it is a function of just Q. And all the difficulties of the spectral problem were transferred to analytical problem of the function Q. Okay, so now we proceed to solving the functional equation. And by spectral theorem, of course, so that if we manage to find the unitary phi of Q, then it is unique, just because the spectral problem is solved in essentially unique way. Okay, so solving the functional equation. So I recall you that it was phi x minus I by over 2, b over 2 equal 1 plus e 2 pi bx phi of x plus ib over 2. So here is no operator problem, just a problem of finding one single function of one single argument. So what we do? So it's already linear, but we can make it even more linear, whatever it means. But here it is a linear in the so it satisfies a homogeneous linear equation. But we can make it an inhomogeneous linear equation easily by applying the logarithm to both sides. Right? So it's maybe logarithm after all is not quite invertible. So to avoid your complaints about that, so let me put it like this and write it log phi of x minus ib over 2 equal log of 1 plus e 2 pi dx plus log of phi of x plus b2. So you see, we took one linear equation and wrote another still linear equation. But there is a huge difference between two forms. Do you see it? Of course, it is inhomogeneous now. But the difference is that if this was linear with non-constant coefficients, this one is a linear with constant coefficients. Right now, this is equivalent to, say, f of x minus ib half minus f of x plus ib half equal log of 1 plus e 2 pi bx, right, where f of x is a notation for log of phi. So you see that here we have a huge advantage that there are no non-trivial coefficients in the equation. It's a different equation with constant coefficients. And what we know of linear equations, whatever difference or differential, with constant coefficients. What is your reaction when you hear equation with constant coefficients? No reaction. Because we know how to solve it, right? If the coefficients are constant, by writing a characteristic equation, for example, or by looking in the form of a linear combination of plane waves in physical terms. But in more mathematical terms, so the linear equation differential or difference with constant coefficients is reduced to an algebraic equation by Fourier transform. That's the main thing. So if we make a Fourier transform here, it will become an algebraic equation. So let us do that. Right? Now we have to make a Fourier transform of that. So we solve it by the Fourier transform. So we have to apply Fourier transformation to both sides. So, okay, here we have an unknown function, so it's a not big deal to calculate its Fourier transform, just a matter of new notation. But on the right-hand side, we have a concrete function. So we have to calculate really the Fourier integral now of the right-hand side. So define I of z to be an integral of log 1 plus e2 pi b x e. So let me see what my Fourier transformation conventions. I applied just the usual kernel, which we use every now and then in the quantum context. But here we use it just in the classical context over real. Right? That's what we have to calculate. But if you look at the integral, you will see a problem. Do you see it? It grows linearly on the positive side, right? It's okay on the negative side, because this goes exponentially to 0. So you expand log, and then the exponential decay in the left-hand side, no problem. But the problem is on the right-hand side, linear growth. So what we do with that, with problems like that? So first of all, we should remark that linear growth is very mild growth. It's a polynomial growth. And this is the characteristic of tempered distributions. And the Fourier transform of tempered distributions are not a problem at all. So first of all, we can think of this as a tempered distribution and just proceed with calculation. But since we are pretending to be analytic, even we are going to go finally to the complex domain, then we can do even better. But this is the equivalent thing. So to go with that into complex plane and shift little bit z into upper half space in the complex plane, then that means that the variable z acquires a little positive imaginary part. But we still integrate over real line, so this grows linearly. But when we add little imaginary part to positive imaginary part to z, so I plus z real part plus I times little epsilon, which is positive. I times I is minus, so it becomes minus 2 pi epsilon x, which immediately becomes exponentially decaying. And in that case, our integral becomes just absolutely convergent. And that's a way, but we have to keep in mind that epsilon is infinitesimal, and that's a way of defining the Fourier image of the corresponding tempered distribution. You just shift slightly upwards, and then keep this information intact in the end. And that's the definition of the Fourier image of the tempered distribution. So that's the thing. But let us do it just in complex way. So assume that imaginary part of z is positive. Then the integral, if we the integral converges absolutely at plus infinity. But let us see if we don't spoil what happens on minus infinity, right? Adding, usually, if we improve in one place, then we sometimes we pay price for other things. Okay, let us see what happens at minus infinity. So let us see. So when x goes to minus infinity, we have a log 1 plus e2 pi b x, of course, like this, exponential decay. And the e2 pi I xz behaves like e. Yeah, let me put absolute value, right? We are asking the absolute convergence. So this behaves like minus 2 pi imaginary part of z x. So we have to put together. So if e2 pi x b minus imaginary part of x goes to 0, then going to 0 is equivalent that b minus imaginary part of x stays positive because x is large negative, right? And the integral absolutely converges. And indeed, with positive b, we are safe now. Thus, for any z with imaginary part of z strictly positive but strictly less than b, the integral converges at plus and minus infinity. Now we can forget about tempered distributions. Just think of complex integral of this kind, with z living in the strip in the complex plane, which is parallel to the real line, just located in the upper part of the complex plane. And just remark that the width of that strip is exactly b, right? That what we demanded from phi, but we wanted it to be symmetric two sides, but still this is a log of phi, first of all, and this is not phi at all, actually, because we are talking about the Fourier transform of some known function. So far, no phi, just, but it's a good sign, a kind of good sign. Already the inhomogeneous part of the function with respect to Fourier transform already behaves nicely, in the sense that it's a Fourier image. It's well defined on that open strip. Okay, so that's our conclusion. And now we can safely proceed to actual calculation. And so we still have a couple of minutes. We can start this calculation. Do you think you are able to calculate this Fourier integral? Okay, so now we calculate. So what we do? Log is not pleasant function, right? We know that. So let us get rid of it. And the way to do that is to integrate by parts. So we put the exponential inside the differential and divide by correction thing, which is 2 pi I z. Integrate by parts. We get the minus integral. We keep this 2 pi I x z over 2 pi I z. Differential applied to log. How about boundary term? Boundary term vanishes because of, we remember that we are here. We are here. So everything absolutely converges. And due to absolute convergence, so we have exponential decay at both infinities, so no boundary terms. And just to prepare the formula to continue with after the break, let us differentiate the log. So let me just write z equal minus. We can pull out 2 pi I z in the front, which is a constant integral e 2 pi I x z divided by e 2 pi b x plus 1. And the derivative of the argument is e 1 more e 2 pi bx and 1 more 2 pi b, right, dx. we can cancel this. We can put B here. Sorry. That's the formula with, and we can put it like this if you want. And that's the formula we will start after the break. Okay, so let's continue. One-dimensional integral. So let us make it symmetric downstairs. So I can remove this minus by moving I2 upwards, IB over Z. And I put 2 here, and you will understand very soon why. I put here cosh of pi b x. So 2 times cosh will be sum of 2 exponentials, but we have to correct here 2 pi I x z plus pi bx. Right? So that's now 2 is explained, dx. Now let us put together the coefficients of x, IB over 2z integral over r cosh of pi b x. Here I'm going to pull out 2 pi I x and write something in the parentheses. So there will be z, of course, which was here. And now here, what we have to put. So 2 means that we have to divide by 2. I means that we have to put another I with minus. Right? So that's a thing. And one more thing. So I want to get rid of that b here. So I scale x by inverse of b. And this b will be absorbed. But of course, it will reappear elsewhere. I over, at least the coefficients is more clear now. Cosh of pi x downstairs, dx. And here, e 2 pi I x, I conserve, but I put the inverse of b inside. So it will be z over b. And that b will go away, minus I over 2. Now, do you know how to proceed any further? Okay, let us. So is there anybody who has some experience with Fourier integrals? No? You never practice Fourier integrals? How about Gaussian integrals? That's better, right? Okay, let us see Gaussian integral. E minus pi x squared, no, Fourier, 2 pi I x z. What is the answer? So if you have do probability theory, with Gaussian distribution. What is the generating function for momenta? It's a Fourier transformation of the distribution, right? But here I choose the spatial normalization. And you know why? Because then the function is stable. Just it is reproduced by the Fourier integral. Okay, so how about this? But with the experience with the first integral, what you would say? I mean, the simplest thing which comes to your mind. To me, it comes this. And it is true. This is another function which is stable by Fourier transform. And actually, these are only two examples I know of which are really just stable by Fourier transform. And there are some, you know, this is very much utilized, right, in physics in particular, or in probability. I don't know what is the role in probability theory of that guy, but in a theory of quantum integral system, this is fundamental object. It describes the distribution of asymptotic distribution of zeros of eigenvalues of transfer matrices in integrable systems. Okay, so, and we have exactly, you see, I just prepared everything to use the second integral right here, just cleared up all the arguments. That without thinking, we just write out the answer. But maybe you will say there is an issue that the argument here is complex. But just here, you can go complex as well. The only thing you have to care about that you don't cross any singularities. As soon as you stay within the analyticity region, the integral still holds. Okay, let us see. We just substitute, right? And this will be exercised, by the way. Pi, and then I just put this. Okay, so what we should be careful about singularities, so we should verify probably that Z is in the safe side, right? But what was the condition for Z initially? So we had the imaginary part of Z was less than B, but bigger than 0, which means that imaginary part of Z divided by B is bigger than 0 than less than 1. Less than 1. And so this is equivalent that 0 less than imaginary part of Z over B minus I over 2. No. Now we have to add imaginary part of minus I over 2 to all three sides of the equality. So here will be minus 1/2 less than 1/2. And this is equivalent to minus pi over 2, imaginary part of pi times z over b minus I over 2 less than pi over 2. I multiplied all three terms by pi. And now why I did all this? Just to collect in the middle the pure argument of Koch here. And the argument of Koch here satisfies that the imaginary part is between minus pi over 2 and pi over 2. But Koch is a cos times I, right? And cos has zeros at plus minus pi, which is exactly safe, right? We stay away of zeros of that function. So everything is correct. But now we can continue. So we can say, at least myself, I have a better experience with cos. So let us transform it to cos. Do you know how to easily transform cos from cos? Just multiply by I, or minus I, whatever, because it is even. Cos pi iz over b plus 1/2. For example, I multiplied by I. I over 2z. And then I write it like this. Cos pi over 2 minus pi z over ib. And now can we use a trigonometric formula which says that cos pi over 2 minus phi is sine of phi. This is cos. This is cos. This is sine. And when we change the angle like this, sine cos interchange. So this is I over 2z, 1 over sine of pi z over ib. And now how we go back and forward when we exchanging sine and sinh, because it is not even, right? It is not that simple as with Koch, but the rule is simple. Look, sinh of ix is I sine of x, and sine of ix is same, I sinh of x. That's easy. Just you pull out I, and that's it. So let's do that. I over 2z, 1 over I, sinh of pi z over b. So I jumped to the numerator, right? Please help me to avoid extra signs. So I think that this is minus 1 over 2z sinh of pi z over b. Correct me if I'm wrong. That's it. That's the Fourier transform of logarithm. Right? This was the I of z. So let us recall what was the equation. So we had f of x minus ib over 2 minus f of x plus ib over 2 equal log of 1 plus e 2 pi b x. And now we have rewritten it f tilde, no, it's a, let's be, to stay safe, let us write it just as it is. E 2 pi I x z dx integral over real line is equal to the Fourier transform we just have calculated, which is this, minus 1 over 2z sinh of pi z over b. And just to remember that the imaginary part of z less than b and bigger than 1. Right? That was the correct calculation for that domain in complex variable z. And now let us treat the left-hand side. And the left-hand side is easier because we don't know what is f. As I said, it is easy because we just redenote things, and that is it. So f of x minus ib over 2 e 2 pi I xz. And here is the assumption about analytic assumption about f plays the role, right? And using this analyticity, oh, right, I managed. Using this, we can shift the integral, right? Now we have used the fact that our f is analytic in the upper half strip. And using this, we shift our integral. So this is the same as R. Yeah, of course, we can just proceed it formally, right? If we put here x in here. So usually to avoid mistakes in while changing the variables, I always put x belonging to the domain. And then after that, I proceed like with an editor in computer. Just a stupid replacement everywhere of variables. Like here. So now I shift x by plus I over b. And what happens? So x plus I over b. So I do it also here. F of x e 2 pi I x plus I over b z dx. Dx, of course, doesn't change because of constant shift. And you see that this is equivalent to saying that we integrate over r shifted downwards by I over b2, or maybe w, right? So the better way to say this. Now it is complex integral. F of w e 2 pi I w plus I b over 2 z dw. And then we can use the fact that f is analytic in the strip. And using this fact, we can move back our contour to the real line by using the fact that we don't cross any singularities, so no Cauchy residues to correct with on the way. That's the thing. or the equal analyticity. Analyticity. Is it correct? So somehow today I have a problem with pronouncing this. Analyticity of f of w in the strip. Imaginary part of w less b. Yeah, so if I put equalities, then some people will be happy, maybe. Okay, so then we write this will be R. Now I put back my variable x. E 2 pi I x plus I b over 2 z dx. And now I can say that this is f tilde of z times E minus pi b z. Where f tilde of x is f of x of z, f of x is just Fourier transform 2 pi I x z dx. As I said, it's easier because we avoid actual calculation by putting tilde, because we don't know the function anyway. The second term is treated similarly, but the only thing which is different, we move all things downwards, right? And but we assume that our function is analytic on the symmetric strip at the positive imaginary parts and the negative imaginary parts. So the same argument. What changes is only the sign of that exponential. So let me just write the answer. So integral f of x plus ib e 2 pi I x z dx becomes f tilde of z. So it's the same. It will be same f. Right, we end up with the same integral, Fourier integral along the real line, but the shifted term will be of opposite sign. E pi b z. Now we put everything together. So I don't know what was this 4 star. So that's 4 star is the equivalent to the equation f tilde of z E minus pi b z minus, you remember there was a minus, so we have to put it here, z equal the right hand side, which is just in the upper right corner, minus 1 over 2z 1 over sinh. What is it? Pi z over b. now we can redenote this. What is it? It is a minus twice sinh pi bz. And remember that everything here we are doing is valid in the strip. Imaginary part of b z is less than b and bigger than 0. Right? Everything was correct in all mathematical senses, only for those z. And as I promised, but this is not me, but as general theory tells us that linear equations with constant coefficients are transformed to algebraic equations in the Fourier world. As you see it here, right? No differences, just a product of f tilde of z with minus 2 sinh pi of bz equal something known. So we can just solve it as f tilde of z equal, so this minus go away, 1 over 4z sinh pi bz sinh pi z over b. And why we are allowed to divide? Because we are here, right? No problem with division. So we solved the problem. Look at this. Because what remains is to write the inverse Fourier transform, and that's it. By the inverse Fourier transform, we have immediately f of x is integral over r. No. Yeah, we will correct it, right? F tilde of x it's gone, but I remember the sign. Minus, right? 2 pi I. Z. Let me put y, xy, dy. That would be the inverse Fourier integral if we would be on the real line, but we are not. Remember that z here should be between 0 and b, and strictly, which means that we have to put here some epsilon, I epsilon. And that's a correct formula for any epsilon between 0 and b. That's the correct formula. And usually what we do here, so if I write y in here, so then we can shift by everywhere, shift epsilon by y by, strictly speaking, we have to say this, right? If we write it like this, then I shift backward by minus I epsilon. And it disappears from here. Now y is just as it is. But maybe it's better now to call it z because it is complex. Sorry. This is not my fault that complex variables are called z's, not y's. Okay, and then we can put it the other side plus I epsilon, right? And then we say that's the other way of saying the same thing. So we integrate we write just the Fourier integral as it is, but z should live in the complex line parallel to real line shifted upwards. And here is a formula f tilde, so I don't think that I have to copy it over there. So you have the concrete answer. But of course, we have to pay the price of all this explicitness. We don't know how to calculate this integral. But who cares if it is concrete integral, right? There are many integrals we don't know how to calculate. But it doesn't mean that they are not useless. But maybe I will write the formula. So remember that this was a log of phi. So now I will write it explicitly because it is always phi of x is equal, that's now special function, phi b, which is a definition exponential. Now no complaints because inverse of log is well defined. They go over r plus I epsilon for z sinh pi b z sinh pi b inverse z dz e minus 2 pi I xz. And usually, so you see pi is everywhere around. So usually we just rescale variable z by pi to look it better. And here z over dz rescaling doesn't change it. So that's a final formula for the solution of the functional equation. So you see, it is a unique, we obtain this way a unique solution. Even though a priori you would say, okay, so it's a difference equation and homogeneous linear difference equation. So you should have a vector space of solutions, as you do always when dealing with homogeneous equations. That's correct, but we had an analyticity condition on phi. And that's the condition which removes this ambiguity. And so this is called this function is called Faddeev quantum dialogue. And remark, nine two. surprisingly, we have a symmetry. Phi b of x equal phi b inverse of x. Look at the formula. It's explicit. But we didn't assume this symmetry in the beginning. You remember we had some functional equation which involved just b's. And we solve it. You know, no question. We didn't put any thing like extra symmetry on the way. But in the end of the day, we have it. And this is called the modular duality. This is a modular duality. Okay, of the theory. And you know, this is a similar type of duality as you probably heard of within theoretical physics, like mirror symmetry, U-symmetry, things like that, dualities, which are every now and then in physics. This is just a reflection of this kind of duality. And you see that as I'm repeating, it wasn't put in the beginning. It came out as a kind of reward just of correctly treating the problem. And but from the point of view quantum theory, the consequence of this is huge, right? Remember that h bar. What was it? H bar. H bar was 2 pi b squared. And now we have observed that. So what is b? B squared. B is now b squared h bar over 2 pi, right? And now what we see here. Function phi is the only place where the parameter b enters. We see that we have a symmetry in the theory between the b inverse, which is equivalent to h bar over 2 pi, exchanged by 2 pi over h bar. But small h bar is a quasi-classical regime. When the quantum theory is weak, we are close to classical theory. But since the theory is symmetric under h bar inverse, up to 2 pi factor, the going classical h goes to 0 is the same as going to extreme quantum, right? When h bar goes to infinity. So this is absolutely fascinating. So the weak quantum, quasi-classics, and the extreme quantum, it's the same thing. Okay, now the theorem. Theorem, okay, 9.1 is maybe doesn't make sense. There will be no any theorems today anyway. The function phi b of x has the following properties. Phi b of x, absolute value, equal 1. for any x in reals. That is good news. Why it is good news? Because the operator, you remember, we need actually the, not phi of x, right? But the phi of q hat. And by spectral theorem, the spectrum is a real line of q. So so the spectrum of phi is a unit circle because of this, which means that our operator is unitary. And now the uniqueness of phi is reaffirmed from spectral side, because the solution of the spectral problem for the right-hand side, which we discussed for the positive self-adjoint operator, a priori is unique spectral decomposition. And this function, which is unitary, so by uniqueness, we have solved this spectral problem. Indirectly, but we did it. Second part, phi of b of x, phi of b of minus x is phi b of 0 squared e pi I x squared for any x. Say, let us stay on reals, but it is more general than that, but anyway, it's enough to look at reals. Phi b of 0, it's a number of absolute value 1, and it's a very nice number, you know. Now I'm not sure what is this number. Oh, yeah. E pi I over 24, b squared plus b minus 2. And just remark 24. Those of you who have seen a little bit of string physics, 24 is distinguished. And actually, no wonder. But 24, not only because of string theory, it's modular forms, right? 24 is distinguished in the theory of modular forms. And the fact that there is a modular symmetry is not accidental. And this 24 comes from that. And the last thing is the phi of b of x admits the analytic continuation to the whole not I, E, right? Or there is E in the end? There is? Thank you. I'm now starting having problems with English. With to the whole C as a meromorphic function. Meromorphic function with poles at IBM plus 1/2 plus IB inverse n plus 1/2 for any mn in positive, non-negative integers. So it's a meromorphic function with explicitly known poles and zeros at minus poles. Minus is a mathematical minus, not the deficit. Yeah, and one more thing. The limit of phi b of x when x goes to minus infinity is 1. So there is a list of 5 properties, but of course it is not the exhaustive list. There will be another quantum theorem about this function. But so far, it is just the analytic part of phi. And you see that it is a really, even if we don't know how to calculate it, we know a lot of it. So we know all the singularities and all the zeros. This is not. This doesn't happen often for an unknown function. Okay. Anyway, we have to stop, and we will continue in 2 weeks, right? Next Monday is 1st of May. It's day off because of Liberty Day, right? Or Day of Workers. So it's a pity, but maybe it's luckily we can have again 2 weeks of break. Yeah. Okay. So see you in 2 weeks. Questions? Everything is clear, I hope, right? I was very clear, I think, today. Okay. Bye.